Hey, this is AP Chemistry Podcast 2.1. We're going to talk about water as a solvent, electrolytes, and then molarity calculations. So you need to know that water is the most common solvent. It's one of the most important substances on Earth. Everybody knows that. And it's important because it can dissolve many different substances. And it does that by being a polar molecule. So if you think of water being a polar molecule, if you look at this picture over here, what you can see is that you have the hydrogens and the oxygens. The oxygen is more electronegative and it pulls the electrons away from the hydrogen. It kind of hogs them. And it ends up with this partial negative charge, which means that your hydrogens are going to end up with a partial positive charge. That positive and negative creates hydrogen bonding within water, which makes it a pretty strong bond. And also the positive and negative partial charges make them really attracted to other things that have these partial charges. So polar molecules really like water because water can attract and make that dissolve. So if we look at this picture here, here's an example of what happens. Say we're taking salt, and that's what this is. So this is NaCl, and we've put it with water. What happens when salt dissolves is that the negative oxygens get attracted to the positive sodiums. So the O's that have that partial negative charge get attracted to the positive sodium ions. And then the hydrogens on the water that have the partial positive charges get attracted to the negative chloride ions. And they just end up surrounding it, and they can break apart that ionic compound, and that's why it dissolves and disappears when you put it into water. All right, so dissolution of a solid in a liquid. What it's saying is ionic substances or salts dissolve in water. When they dissolve, they break up into individual cations and anions. You need to make sure that you're pretty comfortable taking these ionic compounds and breaking them up into their different cations and anions. So how you would do these is, I have ammonium nitrate solid. If you put it in water, you're going to get the ammonium ion, and it's going to be aqueous. And then you're also going to get a nitrate anion, and that'll be aqueous as well. So when they're asking you to show how these things break up in water, you start with the solid, the arrow, and then you show the two different cations and anions that you get. Here's another one. We have strontium hydroxide. This one's a little trickier. You just have to watch out for that 2 there. So strontium has a +2 charge, and it's aqueous. And then we would get 2 of the hydroxide ions. All right. Some vocabulary you need to be aware of. Solute is just the substance being dissolved. Solvent is liquid water. So if we have salt water, the salt is the solute, the water would be the solvent. An electrolyte, in terms of aqueous solutions, is a substance that produces ions in solution, and it conducts electricity. So different types of electrolytes. We have strong electrolytes, weak electrolytes, and non-electrolytes. Strong electrolytes, if you do a conductivity test with them, you're going to see that the light bulb is going to glow really brightly. They're really good at conducting current because they have a lot of ions. So these have lots and lots of ions to conduct electricity. Weak electrolytes, you'll see the bulb glow really dimly. It's not going to be lit up as brightly as it was with a strong electrolyte because there's fewer ions. So there's still some ions to conduct some electricity, but not as much as compared to the strong electrolytes. Then your non-electrolytes, you don't get a current flow. There are no ionic compounds or no ionic salts that will break up to produce those ions, so you don't see it conducting electricity. Here's an example of a strong electrolyte, and that would be salt. So distilled water by itself, just water molecules, does not conduct electricity. The same is true with salt. Salt does not conduct electricity if it's solid. But what we see is that if we do salt water, we do get it to conduct electricity because the water comes in and it breaks these up into their ions, and you get those ions in solution, which allows it to conduct electricity, and you get the light bulb to glow. All right, some general rules when we're talking about strong electrolytes. So soluble salts, strong acids, and strong bases, those are your strong electrolytes. Soluble salts are sodiums, potassiums, ammoniums, and nitrates. Any of those will dissolve and break up into their ions when you put them with water. Strong acids, and this is it. This is the only list of strong acids. So if you can memorize these 6, then you know that if you see any other acid, it's weak. They will also break up. So if you think of hydrochloric acid, we'll go down here. Hydrochloric acid, if we think of it in solution, is H plus and Cl minus. So these strong acids produce hydrogen ions in solution. Same is true with nitric acid. You'd have hydrogen ions and you'd have nitrate anions. That would look like that. So strong acids produce hydrogen ions. Strong bases are going to produce hydroxide ions. So when we're talking about a strong base, we're talking lithium hydroxide, sodium hydroxide, potassium hydroxide. And I listed them in this order because if you look at your periodic table, they say they're the big B. They make up kind of a B shape, just how they appear on the periodic table. So it's kind of an easy way to remember what the strong bases are. All right, and we just talked about a strong acid. It's something that produces H plus in water. And this is Arrhenius's definition, but we'll get to this more in a later chapter. But Arrhenius said that an acid is anything that produces protons or H plus in water. And strong acids will ionize completely. So I don't have any HCl left together as a formula unit or as a molecule. It's broken up completely into its ions. And then strong bases, we already said there's something that produces hydroxide in solution. So a base is a substance that produces OH ions when dissolved in water. And the same is true with strong bases. They're also going to ionize completely. So if you put sodium hydroxide pellets into water, the sodium hydroxide solid is going to break up completely. There will be no solid sodium hydroxide left together. It will break completely up into its ions. Weak electrolytes are your covalent compounds, is how you can think of them. So they exhibit a small degree of ionization in water. This is acetic acid, so your weak acids, your weak bases, anything that wasn't on the list that we just talked about. Weak acids like acetic acid there, it will ionize to some extent. And what we tend to do is draw a double-sided arrow to show that it's in an equilibrium. So we are going to get some H plus and we are going to get some of the acetate anions, but we're going to have a lot of this and a few of these and a few of these. So we use a double-sided arrow to show an equilibrium with that. And then when we're talking about expressing the concentration of a solution, we use molarity. It is definitely the most common. So molarity, big M for the units, is moles of solute per volume of solution in liters. And here's the formula right here if you don't already have it memorized. An example would be if I said I have a 3 molar hydrochloric acid solution, what that means, it could mean that I have 3 moles for 1 liter, or you could say I have 6 moles of HCl for 2 liters of solution. Any ratio that when you divide it gives you 3 will work in this situation. So if we want to calculate the molarity of a solution prepared by dissolving 11.5 grams of solid sodium hydroxide in enough water to make 1.5 liters of solution, what I'm trying to find then is molarity is equal to moles per liter. So I'm given the liters, I'm good there. The only thing I need to do is take this and I need to find moles. So I'm just going to do really basic stoichiometry. I have my 11.5 grams of sodium hydroxide. If I add up an Na, an O, and an H, I'm going to see that I get 40 grams. And that is 1 mole. So if I take those 11.5 and I divide by 40, you're going to get 0.288 moles. Maybe. Okay, then I want to divide by the liters that they gave me. So moles per liter, and if you do out that division, you're going to end up with 0.192 molar NaOH. So Checking significant figures, I needed 3 because there were 3 here and 3 here. All right, this is dealing with concentrations of ions. So we're going to talk about if I put an ionic solid into solution, what am I going to get? How are they going to break up? So give the concentration of each type of ion in the following solutions. So I have cobalt 2 nitrate. And if I think about this, if I have cobalt 2 nitrate, this is going to produce 1 cobalt ion and it's going to produce 2 nitrate ions. So that means that my cobalt, which must have a 2+ charge, is going to be equal to the concentration I already have because there are 1 of these, so the concentration will stay the same. My concentration of my nitrate ions, however, is going to be twice that amount because it produces 2 of these for every 1 molecule of this that goes in. So 2 times 0.5 would be 1 molar for the nitrate anions. Here we have iron, and this must be iron with a 3+ charge. So this iron, because there's only 1 of them, will be 1 molar for its ion concentration. The perchlorate ion, there are 3 of them. So my perchlorate ion, I need to take 3 times 1, and I'm going to get a 3 molar concentration for the perchlorate anions. All right, this question says, which of the following solutions contains the greatest number of ions? In terms of number, I don't really need to go there. I'm just going to focus on moles of ions. So to do that, I'm going to take the liters and I'm going to multiply it by the molarity because that is going to give me moles of NaCl. And then I can multiply the moles of NaCl by the moles of ions that will be produced, by the number of ions that will be produced. So if I take 0.4, and I just converted that into liters, 0.4 liters, and I set up a quick little table. You could also do this using the molarity formula. You don't have to do a table like this. So 0.4, and I'm going to use this as a conversion factor. Remember that molarity really means moles per liter, per 1 liter. So in this case, it's 0.1 moles per 1 liter, which means my 1 liter goes on the bottom, and I'm going to put the 0.1 moles on top. And I take 0.4 times 0.1, and I get 0.04 moles. And I need to multiply that by the number of ions I would produce, and I'd produce 1 sodium and 1 chlorine. So I would take that times 2, and I'm going to get 0.08 as my final answer for that one. Here, we're going to take 0.3, that into liters, and again, it's going to be 0.1 moles on top because it's the same concentration as A. And 0.3 times 0.1 is 0.03 moles. And with calcium chloride, I produce 1 of these and 2 of the chlorides. So I'm going to multiply by 3 because I produce 3 ions, and that's going to give me a final answer of 0.09 moles. All right, iron 3 chloride, take the 0.2 liters. And again, same concentration, so the 0.1 moles go on top, the 1 liter goes on the bottom, and 0.2 times 0.1 is 0.02 moles. And then this is going to produce 4. I have 1 iron and 3 chlorines, so multiply that by 4, and you're going to get 0.08 moles is your answer. This last one is tricky. Sucrose. Sucrose is sugar. Sugar does not dissolve into its ions in solution, so the sugar compound stays together. That means there are no ions, so we can automatically discount that one. It's not going to produce any ions in solution. Then if I look back at these, the winner is B, because that produced 0.09 moles of ions. Okay, another question. Typical blood serum is about 0.14 molar sodium chloride. What volume of blood contains 1 milligram of sodium chloride? I can do this question in just one big stoichiometry problem. I'm going to start with my 1 milligram, and I did that so that I can use the concentration as a conversion factor, because if I remember what we just talked about, it really means 0.14 moles per liter. So in order to use that and to get to volume, I need to get from grams to moles. So milligrams, there are 1,000 milligrams in 1 gram. And then if I go to the periodic table, what I need to find is the molar mass of sodium chloride. So a sodium and a chlorine is equal to 58.45 grams, and that's 1 mole of NaCl. So where I'm at are my grams are gone, my milligrams are gone. I can take my moles of NaCl and I can use my concentration now. I have to put the moles on the bottom and the 1 liter on top. And I do that so that my moles and moles go away. So if I do that math, 1 divided by everything on the bottom, I'm going to end up with a really tiny number, which I should because I'm only talking about 1 milligram, which is not a very big amount. So 0.000122 liters. And I should definitely write that in scientific notation. Times 10 to the negative 1, 2, 3, 4 liters of blood. So that's your final answer. 1.2 times 10 to the negative 4th liters of blood would contain 1 milligram of sodium chloride. All right, next question. How much solid potassium dichromate must be weighed out in order to make 1 liter of an aqueous 0.2 molar potassium dichromate solution? So when we're doing this one, this time we're trying to go from liters back into mass because I'm trying to create this solution in the lab and I need to know how much I need to weigh out of this on the scale. So to do that, I'm going to still use this as a conversion factor just like I did in my last problem. So I'm going to think of it as moles per 1 liter, which means I'm going to use my 1 liter as my starting point. If I use 1 liter as a starting point, then I'm going to leave this right side up how I have it written because I need the 1 liter on the bottom to cancel that out. And that's going to give me 0.2 moles. And then 1 mole, because I can't weigh out moles on the scale, I need to know how many grams that is. I go to the periodic table and I add up all the masses of those things. And I end up with 294.2 grams. Those are gone. I'm left in grams. If I do all that math, we get 58.84 grams of potassium dichromate. So if I wanted to create the solution, I would go find the potassium dichromate, make sure I have that much using the scale. I'd put it into a 1 liter volumetric flask, fill it halfway up with distilled water, and I'd stir and mix and swirl until all the solid dissolved, and then I'd really carefully fill it the rest of the way with distilled water up to the mark. And that's what this is talking about right here. So if you don't know yet, these are called volumetric flasks, and they come in all different sizes. And they're really helpful when we're trying to make solutions with certain concentrations. So these volumetric flasks are good for only 1 volume, and that's what this little mark is on the neck of all of these. If I wanted to make 500 milliliters or half a liter of a solution, I would choose this one. If I wanted to make 250, I would choose this one. So you pick the size depending on the volume of solution you want, and you add the solid or you add the stock solution first. You fill it about halfway up, you mix and swirl, and then you fill it really carefully the rest of the way to the mark. And you want to make sure when we're doing these we use distilled water, because we don't want to get things in there that we aren't anticipating, and that would definitely happen if we use the tap water out of the sink. So distilled water, volumetric flasks, and really careful measurements when we're doing these. All right. The other way, besides using a solid to make a solution, is we can do a dilution. And a dilution is the process of adding water to a stock solution to achieve the molarity desired for a particular solution. So you have to start with a concentration that is greater than what you're aiming for, because you're going to be adding water, which means your concentration is going to be dropping. So you need to make sure your concentration of your stock solution is bigger than what you're going to shoot for at the end. And dilution with water does not alter the number of moles of solute present. So if I had 1 mole of a solute in my first container, if I continue to add water, my 1 mole is still there, it's just more diluted because there's more water in there. So the number of moles doesn't change, and what that does is allows us to set up this really nice formula for dilutions. M1V1 equals M2V2. And we can do that because the moles before have to equal the moles after the dilution. They're not changing. All right, so our question is, what volume of 16 molar sulfuric acid must be used to prepare 1.5 liters of a 0.1 molar sulfuric acid solution? So basically I've really concentrated sulfuric acid right here, and I need to end up with a solution that is not very concentrated at all. And I need to know how much of this should I use. So to do that, we use the M1V1 equals M2V2 that we just talked about. It does not matter if you use liters or milliliters for your volume. It's just if you plug in liters on one side, you're going to end up with liters on the other side. If you plug in milliliters on one side, you're going to end up with milliliters on the other side. So you can just pay attention to that. The molarity of my stock solution is 16 molar, but I am unsure of the volume of it that I need. I do know, however, that I need to end up with 0.01 molar, and I need 1.5 liters of it. So really important that you match things up correctly. All right, all I do is solve for x through really simple math. And if we do all that, we end up with a really tiny number, 9.4 liters. Okay, and I cannot measure that in a graduated cylinder. That would be really hard. Graduated cylinders do milliliters, so I would do a quick conversion to 9.4 milliliters of stock solution. So I would measure out 9.4 milliliters of the 16 molar sulfuric acid. I'd put it into a 1.5 liter volumetric flask, fill it halfway up, kind of swirl it around, and then I'd fill it the remaining way up to the mark, and that's how you would create your solution. Okay, that is the end of podcast 2.1. Make sure you are really comfortable using molarity and doing molarity calculations, and also that you understand what ionic solids do when you put them with water.